So as we begin our next session here, we have Dr. Jeremy Brown from Johns Hopkins University, who's going to be talking to us today about haptic interaction design for telerobotic devices. Whenever you are ready.
Perfect. Thank you, Zane, for that introduction. Thank you, Zane and Marcy, for organizing this. I think this is a fantastic forum. As Zane mentioned, my name is Jeremy Brown. I'm an assistant professor at Johns Hopkins University, where I direct the Haptics and Medical Robotics Laboratory, which is affiliated with the Laboratory for Computational Sensing and Robotics and the Malone Center for Engineering and Healthcare. And today I'm going to be talking a lot about the work that we've done in our lab, looking at haptic interaction design for telerobotic devices. And as I hope to convey throughout this talk, I think there are some strong parallels between the work that we're doing with telerobotics that really do carry over or could carry over into the work that could happen in the virtual reality, augmented reality, mixed reality space. Okay, so given that I'm not sure if everyone here is familiar with telerobotics, I'm going to do a quick primer. So we know that we use our hands, limbs, especially upper extremity, all the time for dexterous manipulation, whether it's grabbing the coffee in front of you, typing on the keyboard for Q&A. We can do good manipulation in the environments that we interact with. There exists, though, a class of environments or different types of environments that are really hard to do direct manipulation in. It could be because those environments are located at great distances from where we are. The environments themselves could pose, hazards or dangers to our body. The environments could be on a different scale than our limbs are, or there could be some other barriers that limit our access, our ability to interact directly with the environment itself. There are also a set of scenarios where the body itself has been augmented in some way. And there we're trying to interact with our normal environment, but because of limitations of the body, direct access, direct manipulation is not possible. Well, in both of these situations, what we need is some sort of interface that takes the intent that we plan to act on the environment and basically carries out that action on the environment ourselves. The original kind of coined term for these types of interfaces are teleoperators, but given the advances in electromechanical systems today, we generally refer to these class of systems as telerobots. So when we think about telerobots as they're commercially available today, we've built robots that are really good at taking the intended action of the operator and carrying out that action on the environment. Because these are robots, right? These robots are outfitted with a number of sensors that do a really good job of managing and measuring the interactions between the device and the environment itself. But really and truthfully, in order to give the operator good dexterous manipulation over that environment, we need to be able to pass these haptic cues or these interaction cues back to the operator. And so this is where a lot of the work in my lab comes in. We're really focused on the haptic interface. So how do you add haptic interfaces to these telerobots to basically restore or provide the operators with this necessary haptic feedback to extend their dexterous manipulation into the remote environment? So now when we look a little bit closer at this kind of triad here, the body, the robot, and then the haptic interface, one of the problems that you'll find is that, especially with commercially available systems, telerobotic systems today, haptic feedback is really non-existent. And then when you look in the work that we're doing in our research labs, my lab included, we're really struggling to reach that, high fidelity haptic feedback. And so a lot of my work and the work of others, across the country and across the world in this space is really thinking about how do we add good haptics to telerobotic applications. I'll quickly argue here that, for the sake of this workshop here, we could simply swap out this telerobot for any kind of interface that interacts or interfaces us to the virtual world. And I think you can kind of see now that these parallels, these parallels between telerobotic applications and maybe virtual reality applications. Okay, so the way that I'm going to split up this talk is I'll spend the first half talking about some work that's recently come out of our lab, bread and butter telerobotics applications, haptic feedback. And then I'll pivot a little bit and talk about some other work that we've done that I think maybe aligns a little bit even stronger, or I should say aligns a little bit more with the virtual reality space, where we have been either investigating VR or using VR in some way to do scientific inquiry. Okay, so as you probably have seen from my little brief introduction here, our lab really focuses on two telerobotic systems. The first is upper limb prosthetic devices, the second being robotic minimally invasive surgery. Most people, it may not be, let's say, common to think of a upper limb prostheses or upper limb prosthetic device as a teleoperator, but when you think about it from the extent that you are operating a distal end effector from some proximal location in your body, then it kind of fits the definition, of a classic telerobotic device. So I'm going to spend a little bit of time talking about the work that we've been doing in the upper limb prosthetic space. And this is some work that's been led by my PhD student, Neha Thomas, and a now alum of the lab, Garrett Hong. So if you were to have an amputation today, you really have two choices in terms of the types of prostheses that are clinically available. The first is a body-powered device. It was invented post-Civil War era. It's really truly just a mechanical system. There's a shoulder harness that you wear, there's the end effector, and then there's a Bowden cable, similar to the cable that you'd find on like a brake for your bike that connects the two. And so movement of the body essentially causes movement of the end effector. On the other hand, we have myoelectric prosthesis, which was invented around the 70s and 80s, which basically uses surface electrodes over muscles in the residual limb to, with amplification, drive the robotic end effector or robotic hand. Now, body-powered devices, just because of their inherent mechanical linkage between the end effector and the shoulder harness, have inherent haptic feedback. There's inherent force reflection between both sides of the device. Myoelectric devices, on the other hand, don't. And so a lot of the work in our lab is really thinking about how do we add good haptic or do good haptic interaction design for upper limb myoelectric devices. So I'm going to talk very briefly about a study that we recently ran in our lab where we were interested in comparing. So there's been a lot of work, and I have to give credit to the number of researchers out there who've been doing work in this space of haptic feedback for upper limb prostheses. What we were interested in is kind of thinking about this from a couple of different ways. One is, so we've done a lot of work in adding, in the research lab of adding haptic feedback to myoelectric prosthetic devices, and we've shown that, hey, it does have some advantages over what we consider to be the clinical standard, a myoelectric device without haptic feedback. But we also wanted to say, okay, how far have we come? And how does this compare to our intact limbs, which we know are just really good at doing dexterous manipulation? And the way we were interested in doing this comparison is kind of thinking about it in two different ways. The first is just what I consider task-based, right? If I gave you an object that had a certain stiffness and you had to squeeze it, and I was giving you haptic feedback of force, how well would you do at recognizing that object by the forces that you receive? Then we also were looking at, well, what is the, let's say, cognitive effort or cognitive or mental load that it takes to actually do that task. And so there've been some studies that had looked at, cognitive measures of adding haptics in upper limb prostheses. By and large, most of these measures have been using things like secondary tasks, which, while provide interesting insights, maybe are not, let's say, don't give the real fine-tuned measure that we were hoping to get. So what we did is, in collaboration with a colleague of mine, Hassan Ayaz at Drexel University, we added this neuroimaging modality called fNIRS, functional near-infrared spectroscopy, which looks at the level of oxygenation in the blood in the prefrontal cortex and can tie that to cognitive load. We ran a simple task in this case where we had three objects, as you can see in the top right, that were essentially visually identical, although you can kind of see at the top there, maybe not so much, but at least from what we could show you, they were visually identical. And all we did is mix different ratios of silicone to kind of get them in three different compliances: soft, medium, and hard. In our lab, we have this mock prosthesis, which you see in the middle left figure here, which is just a voluntary closing prosthetic prehensor with a prosthetic cuff that's built, with a little bulge at the end so you can put your fist in it. And that's because a lot of our work in this prosthetic space, we do a lot of testing with non-amputee participants. Because essentially, by putting your hand in this prosthetic cuff, for the sake of experiments, we can turn a non-amputee into an amputee. And kind of given all the work that has been done in the space of adding haptics, we decided to stick with something that was easy implementable, vibrotactile feedback of grip force. And so we have a piezo-resistive force sensor that sits on the gripper of the prosthesis, and we feed that force back to the user through this vibrotactile actuator. And then we use that same piezoresistive force sensor on the fingertip to be able to measure the force interactions when the participants were grabbing the objects directly with their hand. And in the bottom right, you're just kind of seeing the setup where you've got this box or this curtain that kind of occludes vision, so you can't really see the deformation. Participants were supposed to look at the screen, not what was going on with the prosthesis. So we're really focusing in on just having what is the utility of the haptic feedback from both the task performance as well as the cognitive load measure. And so what did we find? Well, as you can see from this graph here, that because we had 3 objects, right, we would pair these objects together. And the experiment was really, we'd give you a pair of objects, soft, medium, soft, hard, or hard, medium, and you had to identify which of the 2 objects that we gave you was the stiffest. You can see that our results varied by what the object pairing was. So for the sake of and clarity of argument here, I'll just focus in on one comparison, and that is of the soft medium objects. And what you find from a task performance perspective is kind of in line with what you would expect, right? The natural intact limb, our hands, which is highlighted here in the blue bar, is perfect, right? I mean, the error bar is essentially 0 here. Participants, were almost with, clear perfection, were able to identify and differentiate between the soft and medium blocks. On the other end of the spectrum, if you look at the yellow polka dot here, this is the clinical standard prosthesis, so a myoelectric prosthesis without haptic feedback. The performance rate was essentially guessing, right? Because at every task, you had the choice between 2 objects. And so if you just randomly guess, you would get about 50%. And that's what we found. What we also found is that when you add this haptic feedback in, just simple haptic feedback of grip force, performance got significantly better, right? It's approaching what we can do with the intact hand. The task is fairly simple, but at least it's showing that there is some added utility from a task performance perspective of adding haptic feedback into these interactions in terms of prosthesis. Okay, so that's great. But then the question becomes, did this added task performance come at some cognitive cost? And what we're seeing here is the result. So the fNIRS sensor that we use had 4 channels that looked at both right medial, right lateral, and left lateral regions in the prefrontal cortex. Here you're looking at just left medial. And again, I'll kind of, for clarity's sake, get rid of all the combinations except for the soft medium combination. And by and large, what we found is, again, as kind of interesting and as somewhat as expected, right? And so what you're looking at on the y-axis here is the change from baseline. So before we did the task, we asked participants, we took a baseline measure of their oxygenated hemoglobin, and then we measured it in the task while you were actually doing it. And what you see is that for the intact hand, the blue bar again here, the change is relatively nil, right? Change from baseline is almost 0 in this case, right? So very small change from baseline, which you would expect. We use our hands and our limbs all the time, so it makes sense that the mental effort to do this task is not high with our intact limb. On the other hand, if you look at the yellow polka dot, again, the clinical standard here, myoelectric prosthesis, the change is very large, significantly larger than either of the other 2 conditions. And then when we look at what happens when you add the haptic feedback in, we see that while we are significantly higher than the intact hand, the natural limb, we're also significantly lower than the clinical standard prosthesis. So the kind of story here is that there is some utility to adding haptics into your systems, both from a task performance perspective, but also from a cognitive load perspective as well. Okay, so that's kind of some work that I wanted to highlight really quickly in the upper limb prosthetic space. I'll move on now into the work that we've been doing in the robotic minimally and very invasive surgery space. And this is some work that's done by my graduate student, Sergio Machaca, a former alum of our lab, Eric Cow, and another former alum of our lab, Amy Chi. So we talked a little bit about teleoperation and the idea that really good teleoperators or really good telerobotics should have good control, right, from what the operator is, where the operator is controlling device to the remote device itself, but then also good haptic reflection, right? So any interactions that are happening, in the device, or excuse me, on the remote environment, are reflected back to the operator so they can do good dexterous manipulation. Well, by and large, most clinical systems actually don't have this haptic feedback, as I've mentioned. So what we were interested in is really, well, okay, if we add haptic feedback, and again, our lab is nowhere near the first lab to investigate, the benefit of adding haptics into telerobotic systems. The previous presenter, Alison Nakamura, has done a tremendous amount of work in this space. What we were interested in here with this particular study is looking at what is the benefit or the trade-off that comes in terms of the accuracy of doing a task if we add haptics, and then maybe the consequence of the penalty of the time that it takes. So what does the speed accuracy trade-off look like when you add haptics? So we use a simple task here called the ring roller coaster task, which again, as you can see here, it's just a ring on a little track, and the objective is to move the ring around the track without making contact and generating a lot of force on the track itself. This whole track is sitting on top of a force torque sensor, which you can see the cable coming out of out of the system. And then what we do is we take the forces that we measure and we display them through these little tactile actuators, which are these devices invented or created a while ago by Andrew Stanley and Catherine Kuchenbecker, which basically act like, you can imagine it as like a wristwatch that you basically take your watch and just tighten the strap on. And we tighten that strap in proportion to the amount of force that we measure from the system. So the larger the forces that are measured, on the task board, the tighter the strap, let's say, gets pulled or actuated on the wrist. And so you'll see that there are two actuators here because this was a bimanual task, and we separately fed forces from the left instrument went to the left actuator, from the right instrument went to the right actuator. We ran a study where we basically had 20 participants. Half of that group got feedback, half of the group didn't. We did 12 trials. We just wanted to see, okay, what happens if we give you haptic feedback from the beginning? What happens if we don't? And we let you go for 12 trials over and over and over again. How well do you do at this task? Okay. So the two measures that we looked at were both, again, remember speed, accuracy here. Speed, of course, is just the duration. How long did it take you to do the task? Accuracy here, we represented as force. What is the amount of force that you produced on the task itself? And what we found, and you're looking at the results of a generalized linear mixed model here, show that when it comes to force, and we've had to log transform everything just due to normality, the feedback group produced significantly lower force over the course of the entire 12 trials, than compared to the no feedback group. So significantly less force with the feedback group, which sort of intuitively makes sense. They're getting real-time feedback of the forces that they're producing, and they're using this information in real time to basically monitor and adjust so that they produce as little force as possible. But now, does that come with a consequence or some cost related to how long it took them to do the task? And what we found is that the answer is yes, but. So at the beginning of the trial, right, the feedback group, which is highlighted here in red, started out significantly slower than the no feedback group. But what's interesting is that while both groups got faster over time, our results show that the feedback group got significantly faster or decreased the time that it took them to do the task at a significantly faster rate than the no feedback group. So, we don't know what happens here at the end of 12 trials. If we went to trial 13 all the way up to trial 20, maybe the feedback group would plateau, or maybe they would continue to decrease their time such that maybe, it could be possible that their forces overlap with, their durations overlap with that of the no feedback group. And so this kind of shows that more investigation is needed to kind of figure out what are the long-term or longitudinal consequences of adding haptics into systems like this. Okay, so that kind of ends the essentially the work that we've been doing, just kind of haptic feedback for kind of standard telerobotic teleoperation and telerobotic devices. I'm going to switch gears a little bit and still continue to talk in the vein of teleoperation and telerobotics, and try as best as possible to introduce a little bit of the work that we've been doing in the VR space. So this next study that I'm going to show you is some work that was done by a visiting student of mine, Guido Cascianiga, who was a student at Politecnico di Milan at the time, is now a PhD student at the Max Planck Institute for Intelligent Systems. And during the time that he visited my lab, we kind of really got interested in this idea on surgical training and the various ways that you can do surgical training. And so I'm just going to kind of preface this by saying that this result, I think presenting this result as somewhat of a reflection point for those of us in the field looking at VR, AR, mixed reality applications as a point of consideration. So when you look at surgical robotic training kind of clinically, or if you look at hospital systems across the world, right, there are kind of two flavors to training. The first is virtual reality training. So there are these desktop trainers like the Mimic trainer that you see here, or Intuitive Surgical makes a trainer called the DVSS. that allows trainees to sit at the console and practice tasks. And so the benefits of VR in this case is that you can practice complex tasks without, using expendable resources. You can do the task over and over and over and over again. So there are a lot of reasons why I think hospital systems have adopted these VR simulated trainers. At the same time, though, there's a lot of training that still goes on the robot itself, and there's evidence to show that training on the physical robot is still somewhat considered the gold standard, because performance again happens on the physical robot. Well, we were kind of interested, in answering this question of, are they equivalent, right? Is training in VR exactly the same thing, or as training in the physical world? And so Guido built this really nice setup, and I'll play this video, where basically using the DaVinci Research Kit robot, which is an open source platform built off of the Intuitive Surgical DaVinci Telerobotic system. He basically built this task, which is around needle driving, that has both physical and virtual analogs. And so you're seeing the virtual analog on the left side, the physical analog through the robotic endoscope on the right-hand side. This video will just show you, I mean, they're not exactly the same, but we tried as best as possible to mimic the behavior in both of these videos, but you can see that essentially the systems look the same and basically operate the same. And so the task was to grab one of these suture needles and drive it through the rings. And if you deflected any of the rings, we would measure those deflections and then use this little LED strip around each of the rings to let you know how gross of an error you were actually making. So I'll let this video play. Maybe, there we go. Okay, so what did we find? So we ran a study where we basically had, again, two groups of participants. We broke them up, group A, group B, 9 participants in each group, and we ran them through this protocol. Both participants did baseline measures where they basically did the task over and over for 15 trials in their respective platforms. So group A started off in the inanimate platform, so that's the real physical system. Group B started off in the VR platform. Then we did a training session where we basically had them repeat the task over and over and over again at various speeds, at 3 different speeds. And I can talk about this maybe in the Q&A, why we were looking at these 3 different speeds. It relates to another, let's say, arm of this study that I can elaborate on later. But basically 40 repetitions of this trial, again, in the same platform. Then we did an evaluation. So what was the benefit of training in that platform? Now we evaluated in that same platform. But then at the end, what we did is we crossed the groups. So if you did all of your baseline training and evaluation in the inanimate platform, we then asked you to do another evaluation in the VR platform. Likewise, if you did all of your baseline training and evaluation in the VR platform, we then asked you to do another cross evaluation in the inanimate platform. And so what did we find? Well, as I mentioned, we asked participants to do this at 3 different speeds. So I'm gonna abstract out and just talk about one speed in particular, the moderate speed, because this is the one that most participants actually preferred anyway. It's kind of the natural motion, our natural course of movement. And what we found is that, lo and behold, in both cases, participants got better in each platform, right? So from baseline to evaluation, the red to the green here, in both groups, both the VR and the inanimate, participants got significantly better. But what's interesting here is that when we asked them to switch or cross platform, so to perform or evaluate in the opposite platform, what we found is that for inanimate training, when participants moved to VR, their scores, and here we're looking at the y-axis of an error metric that looks at the total deflection of the needles, their errors didn't change significantly, at least, right? They stayed about the same as they were in the evaluation on the inanimate platform. However, when you look at the results in the virtual world, participants, when they moved to the physical system, their errors got significantly higher. So their performance got significantly worse. And so I present this result to you, to posit to you, those of you working in the VR space, to be very cognizant of and always remind yourself and continue to think about, there is somewhat of a difference between the physical world and the VR world. And I know a lot of our research is interested in trying to make the VR world mimic as best as possible the physical world. But I think we need to be mindful and cognizant of the fact that these two may not always be the same. And so how do we ground them in the right way? I think is really important for researchers, both in the VR space, but also in the haptic space as well. And that's because, a lot of our work in the haptics world, as I'll talk about here, actually involves VR to do scientific inquiry. So I talked a little bit about the work that we did in prosthetics and the work that we did in minimally invasive surgery. This next example that I'm going to share with you briefly is some work that was done by both my student Garrett Ung and Sergio Machaca, where basically looking at the work that we've done for the last couple of years in this space, they kind of realized that most of the results that we find, or most of the experiments that we run, are these single modality things, right? So measuring force on a prosthesis and presenting force back through sensory substitute of vibration, or measuring force in a surgical robotic device and presenting it back to the user through the sensory substitute of squeezing at the wrist. But when you look at the tasks that we do in the world, kind of just using our arms and our limbs, right? They don't just represent these single things like forces. They're this multitude of haptic cues, right? So it could be the case that it could be the case that we pay attention to the pressure, right? Because pressure is really important in certain tasks. It could also be the case that we pay attention to the way things slip between our grip, if we're gripping an object. It could be the case that we pay attention to vibrations, because vibrations give us indications of how well we're doing or if the task is success. And it could also be the case that we need to know where we are and we need to be able to localize our position. And we also use constraints on the environment, or forces and impulses that basically tell us whether we've done something the right way or not. Well, I think it's kind of worth highlighting here that what I'm saying is that what we really need to be thinking about is these multimodality cues. Again, I'm not going to claim, I will say that our work is building off of the work of many other labs that are starting to look at this multimodality displays, namely Marcy O'Malley's group, the Mahi lab at Rice. I would also say that these multimodality things need to be of consideration to those of us working in the VR space, because truly, if we're trying to replicate the physical world, we need to be thinking about multimodality displays. Well, we started thinking about these multimodality displays kind of from the perspective of telerobotics and teleoperation, thinking that, okay, back to this original primer that I showed, really when we interact with our telerobot and our telerobot's interacting with the environment on our behalf, what we should really be displaying back to the operator is this myriad of haptic cues that they need in order to do closed loop, fine, dexterous manipulation. So we decided to come up with a task that we thought, was relatively interesting, while it is a little bit contrived. And it can be highlighted here by thinking about these three cases that I've shown, right? You think about an egg, right? Egg requires fine dexterous manipulation, right? You squeeze too hard, it breaks. You don't squeeze hard enough, it slips. But there's also, highlighted here by tying shoes and the suturing example, there are cases where while we're holding something, the load on that thing that we're holding increases over time. So as a thought experiment, we said, okay, imagine now that I was asked you to hold this egg. And while you were holding this egg, I tied a string to it and basically started pulling down on it. As a result of that, right, you have to either, again, grab harder to keep the object from slipping, which if you grab too hard, there's a penalty, the object breaks. Or if you don't grab hard enough, the object slips. In either case, failure means broken eggs. That's not really conducive in a laboratory environment. And so we said, okay, well, how else can we study this? And so we turned to VR in this situation. Now, granted, I'm going to say our VR is very limited here, two-dimensional, but essentially what we're showing is that we can use VR, virtual environments in this case, to actually study some of these principles that we think are really important. And so this experimental setup here that you see is looking at both from a teleoperation, like a Da Vinci standpoint of doing virtual gripping of these objects that have increasing load force, and then also from a prosthesis standpoint, where you're using an EMG electrode interface to basically grab the object. We're really concerned about what happens when you grab the object and we have to change the load force on that object, kind of in real time. How do you adapt to it? So this real-time continuous haptic feedback is what our group is, or multimodality haptic feedback is what our group is interested in. Okay, so I'm going to wrap up really quickly and just say that I've kind of showed you the where we've investigated VR and tried to see how does VR compare to the real world when it comes to something like surgical training. We then use VR to be able to do scientific inquiry around what is the added utility of multimodality haptic feedback in current, let's say, telerobotic systems. We've now, some of the future work that I'll just talk about in the upper limb prosthetic space, we really started to play around with this new I don't know if you would call it class of devices. It's not really a class of devices, but I had a student, Ethan Miller, in my lab, and Ahim Ryorochi Amanze, basically build this anthropomorphically driven prosthesis, which basically uses antagonistic tendons to do both extension and flexion of a prosthetic hand, because we're really interested in allowing amputees to modulate their impedance of their hand in real time, because it's been shown that you would want to modulate. We modulate the impedance of our limbs in real time for a number of tasks. And then separately in our lab, we've kind of abstracted out this surgical robotic space and just looked at pure telerobotics and said, what is the, the impact of the dynamics between the two sides of the teleoperator on your ability to do perception of the remote environment. And then, of course, because many of my other colleagues, labs were shut down over the summer, we couldn't really run user studies. We really started to think about ways in which we could use VR to really expand beyond these two-dimensional VR, virtual environments to three-dimensional virtual environments in our perceptual and performance-based studies. So with that, I just want to thank all the students in my lab who made this possible, my funders, and then of course, if you want to learn a little bit more about the work that we're doing in our lab, here's our lab website. So with that, thank you.